From the moment we first gazed up at the night sky, we have been dreamers. The stars have always whispered to us, mysteries in motion, stories told in light. And among those stars, we've found inspiration, longing, and questions. How far can we go? How fast? And what power must we harness to break the bonds of Earth and reach the realm of the stars? Even now, with decades of spaceflight behind us, we are barely skimming the edge of our own solar system. Voyagers 1 and 2, our most distant ambassadors, travel at mere fractions of a percent of light speed. They are on journeys measured in tens of thousands of years. And even with the boldest rockets we can build today, Proxima Centauri, the closest star beyond our sun, remains impossibly far. If humanity is ever to leave its cradle and voyage into interstellar space, we will need a revolution in propulsion. A leap not of thousands of kilometers per hour, but millions, perhaps even a fraction of light speed itself. That leap may one day come from the unlikeliest of places, from a force so powerful, so absolute, that it annihilates the very matter of our universe. This is the story of antimatter propulsion, and the future it could unlock. At the smallest scales of the universe, nature reveals a hidden symmetry. For every particle of matter, there exists an opposite, its antimatter twin. This is not science fiction, it is quantum fact. The positron, for example, is the mirror image of the electron. Same mass, opposite charge. And when the two meet, they do not simply bounce off each other. They vanish, converting their entire mass into energy. This process, known as annihilation, is one of the most efficient energy conversions possible in the universe. Unlike chemical reactions, which extract energy from the rearrangement of electrons, or nuclear fission, which splits atomic nuclei, antimatter reactions turn all of the participating mass into energy in accordance with Einstein's famous equation, E equals mc squared. That means just 1 gram of antimatter, when combined with 1 gram of matter, would produce roughly 90 terajoules of energy, the equivalent of more than 20 kilotons of TNT, or the blast yield of the bomb dropped on Hiroshima. But where does antimatter come from? In nature, it's rare, produced in high-energy environments like lightning strikes, radioactive decay, or cosmic rays interacting with Earth's atmosphere. In the lab, we can produce antimatter in particle accelerators, 1 atom at a time. Yet while it is difficult to create and even harder to store, the physics is clear: antimatter is real. It's been created, observed, and measured. And if harnessed, it could be the most potent fuel source ever conceived. Rockets, as magnificent as they are ultimately limited by the very fuel they depend on. The physics of propulsion demands that to go faster, you must carry more fuel. But that fuel adds mass, and that mass requires even more fuel to move. It's an unforgiving cycle, described by the Tsiolkovsky rocket equation, which engineers know all too well. Chemical rockets, the kind that lifted Apollo to the moon, burn quickly and with great force, but they are astonishingly inefficient. Their specific impulse, a measure of efficiency, is typically less than 500 seconds. For comparison, an antimatter engine could theoretically exceed 1,000,000 seconds. Current rockets are good for getting off Earth and into orbit. They're good for reaching the moon, Mars, or even the outer planets. But they're not suited for interstellar travel, to reach another star in anything close to a human lifetime. We need propulsion that's orders of magnitude more powerful. Even the most advanced designs in development, like nuclear thermal propulsion or fusion-based drives, face enormous engineering hurdles. They may get us to Mars in weeks instead of months, but they still fall short of what's needed for true, deep space exploration, which is why antimatter, despite its exotic nature, is not merely a curiosity, it's a necessity. If we wish to cross the oceans between stars, we need the energy of suns in the palm of our hands. And that's what antimatter promises. The dream of antimatter propulsion is both elegant and terrifying. At its heart is a simple concept. When matter and antimatter collide, they annihilate, releasing a flood of high-energy photons, usually gamma rays, and sometimes heavier particles like pions. In theory, an antimatter engine would harness these products, channeling them through a magnetic nozzle or a reaction chamber to generate thrust. Some designs propose mixing antiprotons with deuterium fuel to ignite tiny, controlled fusion reactions, each one producing more thrust than a conventional rocket ever could. Others envision beamed core engines, in which the annihilation products are directed out the back of the spacecraft at near-light speeds, producing tremendous momentum. These designs could, in theory, push a spacecraft to 10%, even 50% of the speed of light. At those velocities, journeys to nearby stars become achievable. A robotic probe to Alpha Centauri might take decades, not millennia. Human missions, while still far-fetched, could move from the realm of fantasy into the realm of distant planning. The challenge lies not in the physics. It works on paper, but in the engineering. How do you store antimatter without it touching anything? How do you control such a volatile reaction? And how do you build a ship that can survive both the immense power and the harsh environment of near-relativistic travel? These are questions we've only just begun to ask. For all its promise, antimatter propulsion remains just beyond our grasp. The greatest challenge, by far, is production. Currently, we can only produce antimatter in particle accelerators in minute quantities. CERN, for example, can create antiprotons, but at a cost of trillions of dollars per gram. At that rate, producing even enough antimatter for a small-scale experiment is a colossal investment. Then comes storage. Antimatter cannot touch ordinary matter. It annihilates instantly on contact. So we must suspend it perfectly in a vacuum using magnetic and electric fields. These so-called pinning traps work for holding tiny numbers of particles for short periods. But scaling them up to hold usable amounts, let alone in the volatile environment of a spacecraft, is a monumental technical hurdle. There's also the issue of containment safety. A failure in a fuel tank for a chemical rocket results in fire. A failure in an antimatter containment system could unleash enough energy to vaporize an entire spacecraft. And finally, we must consider the issue of thrust control. Creating a propulsion system that can throttle, steer, and safely modulate antimatter reactions is a feat of extreme precision. All of this makes one thing clear. While antimatter propulsion is not beyond the laws of physics, it is far beyond our current engineering capabilities. But that does not mean it always will be. The path to antimatter propulsion will not be paved overnight. It will require decades of breakthroughs in particle physics, materials science, magnetics, and space systems. But the seeds have already been planted. NASA, the European Space Agency, and even the U.S. Department of Defense have all funded research into antimatter storage and applications. Private companies and university labs continue to make strides in miniaturizing traps, improving production efficiency, and developing simulations for future spacecraft designs. Some scientists envision hybrid engines, where minute quantities of antimatter serve as ignition sources for fusion-based propulsion. Others imagine ultra-efficient antimatter propulsion systems used only in deep space, after a ship is launched by more conventional means. And beyond that horizon lies the truly transformative dream, an antimatter-powered interstellar probe, a mission that could leave the solar system, visit another star, and return data, all within a single human lifetime. That may seem like a fantasy, but so, too, once was the moon landing. And in science, yesterday's fantasy often becomes tomorrow's engineering.